Alrighty, hey everyone, welcome to today's session. My name is Farzad Sunavala. I'm part of the Azure AI Search product group, and over here I have my buddy Laurie Voss, VP of Developer Relations at LlamaIndex. And today we're going to talk about advanced RAG with Azure AI Search and LlamaIndex. And with that, I'll hand it to Laurie.
Thanks, Farzad. Hi, everybody. Thank you for showing up for the last session on almost the last day. You are the few, the proud, the brave. What are we going to be talking about today? If you're still new to RAG, Retrieval-Augmented Generation, you've probably heard a lot about it at this conference. We're going to do a super quick recap of what RAG is and how it works, but not super deep because you've probably been hearing about RAG a lot. Then we'll talk about how RAG can fail and why it can fail. And what we can do about that. And then we'll talk about what LlamaIndex is very briefly and how it works with Azure AI Search. And then we'll go into a demo of how LlamaIndex and Azure AI Search work together. So Retrieval-Augmented Generation is, at its heart, a response to a fundamental limitation of LLMs. LLMs are trained on vast quantities of data, but they're not trained on your data. So you have to give them your data, but you have more data than an LLM can absorb at once. And even if your LLM had an infinite context window, you wouldn't want to give it all of your data at the same time because it wouldn't know what was important. You have to be selective about what data that you give an LLM so that it can focus on that data and reduce hallucinations and reduce extraneous information. RAG gives you a way to do that by using semantic search, search by meaning. Using technology related to LLMs called an embedding model, you convert your data into arrays of numbers called vectors. The total set of available vectors is called vector space. So this conversion is known as embedding your data into vector space, and the resulting numbers are called embeddings. This is 3 degrees of indirection away from the thing that we actually did. Why do computer scientists name things that way? I don't know, but they do. So when you want to answer a query, what you do is you embed your query in the same way that your data was embedded, and it ends up in vector space mathematically nearby to the semantically related information. Using relatively simple math, you can then retrieve the data that is most like your query and send this data and your query to the LLM. So that is the theory. Let's talk about how you build a RAG pipeline in practice. First, you have to ingest your data. You have to parse it into chunks. You have to embed each of those chunks of data. And then you store them in a vector store, like Azure AI Search. Then you use a query to perform semantic search on the chunks in your vector store, retrieving the most relevant, most related chunks. You take those chunks and your query, and you hand them to the LLM, and the LLM generates a relevant answer to your question. In LlamaIndex, you can get this done in 5 lines of code. But the point of this talk, indeed the point of LlamaIndex in general, is that there is more to this problem than naive RAG in 5 lines of code. Naive RAG is limited. It tends to work for simple questions over small sets of documents, and there are a number of ways that naive RAG can fail. One task RAG is not great at is summarization. Just by design, what RAG is doing is it's doing a query. It's looking for data that is related to your query. So if you ask it for a summary, unless there's a chunk in there that is called, I am the summary of this document, it's not going to find anything. It's going to find some random chunk of your document that is not a full explanation of what that document is. That's just not what RAG is designed to do. Another failure mode that naive RAG has is comparison. If you give it a comparison question of comparing A and B, it's going to find chunks about A and chunks about B, and it's going to hand them off to the LLM. But the LLM isn't necessarily going to know which chunk is about A and which chunk is about B. And you can often see that when you ask comparison questions of a naive RAG pipeline, it will confuse the 2 things it's supposed to be comparing. And in general, naive RAG is not good at multi-part questions. It tries to do everything all at once. It has a query, it has a response, and you get what you get in that one response. But that isn't to say that naive RAG is useless. In fact, it's extremely useful. It is necessary, but not sufficient. Lots of tasks require semantic search, but lots of tasks require more than that. So how do we go beyond the limits of RAG to fully utilize the power of LLMs? There's 2 avenues of improvement that we can take. The first is to improve the data quality. That's one of the reasons that LlamaIndex that we built llamaParse. It is a service that dramatically improves your data quality by preparing your documents into a form that is most easily consumed by LLMs, as we're going to talk about later. The second way that we're going to be talking about more today is by making your querying more sophisticated. We're mostly going to be focusing on how to improve our querying by using agentic strategies today. So what is an agent? Well, first, it's a term that is overused in the industry to the point of meaninglessness. So when I use the term agent, what I mean is a semi-autonomous piece of software that you can give a goal, and it's going to work to achieve that goal without you knowing in advance exactly how it's going to get there. Let's talk about agentic strategies and how we can build them into our system, working our way up to a full agent. By building Agentic RAG, you can address all of the limitations of naive RAG. You can make your queries multi-turn. You can have your agent understand the question and plan how to get the answer in multiple steps. You can make RAG just one of many tools that your agent can use to answer questions and take action. And you can use reflection to figure out if the response that you've generated is adequate, and if not, it can self-correct and try again or course correct. Getting all of that done is a lot of work, but that is the work that LlamaIndex gets done for you. The strategies I'm talking about exist on a spectrum of complexity, from simplicity to complexity, and also from cheap to expensive. Cheap in terms of the number of tokens used, the number of LLM calls used, and also the amount of time required. So you don't necessarily want to leap to a full agent every single time you're making an application. You have to trade off latency and expense when you're building an application. So let's break down these agentic strategies. The first up is routing. This is the simplest form of agentic reasoning. Given a query and a set of basic tools, the router uses the LLM to select which is the best to answer the question. This can solve the summarization problem because you can make one of the tools available a summary of the document. So by using query understanding, when it gets a question that the LLM recognizes as being a request for a summary, instead of attempting to do naive RAG, it will just go straight to the summary and say, here's the summary. The next tool that we can add to build up an agent is memory. This is theoretically simple. As you run queries, you add those queries and those responses to your history, and you pass in your history as part of your query to the next, in the next turn. This gets more complicated as your history grows longer and begins to overflow your context window. You have to start being selective, you have to start condensing your history, or you have to put your history itself into a RAG index and retrieve the bits of your history that are most relevant to your query rather than giving the entire history every time. The next thing we can add is one-shot query planning. This takes a complex question and breaks it up into simpler questions. And then it runs all of those simpler questions in parallel. It gets the responses to all of those simple questions and gives those to the LLM. And then the LLM creates a coherent response that is the aggregate of all of those simpler question responses into a single answer to your question, based on far more context than trying to do it all in one shot. The way that we make all of that happen is one of the biggest parts of agents and agentic RAG, which is tool use. LLMs allow you to describe an arbitrary API that they can then infer the parameters of. You can then get your LLM to call that API, and the result is that you can get not just an answer to a question, but you can get the state of the world, and you can take actions in response to what the LLM has decided to do. One of the other things that tool use allows you to do is adapt your query to the tool that is being used. In this example, in text to SQL, for instance, you can change your natural language query into a SQL query, or if your query is, if your query implies that you should be making a calendar appointment, it can call a calendar API and natively create a calendar appointment. So what we've seen so far is the basic agentic strategies, but they are just the minimum necessary to create an agent. We need to go further. Let's make it multi-turn. Let's give it reasoning and planning. Let's give it reflection, and let's talk about how we get all of those things done. There's 3 types of agentic reasoning loops that I'm going to talk about today. There are lots more than that around. I want to talk about sequential, DAG-based, and tree-based reasoning. These also live on a spectrum from the simplest and the cheapest in sequential to the most complex and expensive variant. So let's talk about sequential. The first thing you do is you generate your next step given your previous steps. This is sometimes known as chain of thought. One of the most popular patterns here for agents is called REACT. Not React the web framework, but reasoning plus action. In REACT, the agent generates a distinctive pattern. It generates a thought, and then it comes up with an action based on that thought, based on an observation of what is going on in the world. It does what it thinks is the next proximate step to achieve its goal. And it stays in a loop coming up with what should my next step be, what should my next step be, over and over until it achieves its goal or it gives up. This is very simple but can be very effective. The next step up in sophistication is a DAG-based planning agent. To back up for a second, a DAG is a directed acyclic graph, which, if you're not familiar with it, you can think of as like a flow chart. It's a series of lines and boxes connecting you from your origin point to a goal. If your problem is simple enough, it's possible that your LLM can come up with a plan from start to finish of how to achieve its goal. And accomplish that goal by following the steps in this directed acyclic graph that it's come up with. A critical part of this planning process is the ability to replan if things don't work out. So it will take actions, it will observe whether or not the state of the world is matching what it was expecting to happen, and if it doesn't, it can replan. This ability to self-evaluate is called self-reflection. You can do it by giving it an objective function that it can run to say, am I closer to my goal? Or you can get the LLM to evaluate itself and say, does it look like I have got closer to my goal than I was before? But still, DAG-based planning works best when the task is sufficiently constrained that there's a clear route from your origin to the goal. Some tasks aren't like that. Some tasks are too complicated. And that is when you get to tree-based planning. There are several different variants of this, including tree of thought, reasoning via planning, and language agent tree search. And they have some fundamentals in common, which is that they don't know in advance how they're going to solve the problem. What they do instead is they come up with several possible actions, and then from each of those possible actions, it extrapolates what will the state of the world be after each of those actions, creating a few branches to begin with. For each of those branches, it repeats the process, coming up with new actions and new states of the world until it has generated a tree structure. Once it's got this tree, which can be arbitrarily long, but is usually not too deep, it will observe which of these leaves of the tree is closest to the goal state, and then it will trim the tree and start again with the tree planning process from the leaf that was closest to the goal. All of these strategies that I've been talking about can be overwhelming, so let's break it down into some crawl, walk, and run techniques for improving data quality and improving query sophistication. For data quality, the basics are splitting and chunking. The next step forward is improving your parsing, for instance, with a service like LlamaParse. While the advanced technique is to use agents which look at your data and enrich it prior to querying. For query sophistication, the basics are things like rewriting and re-ranking your queries. And the next step forward is planning your queries and splitting them up. And the advanced solution is self-reflection, which I was talking about, to see if your query results are adequate and course correct if they aren't. Now let's talk about how LlamaIndex and Azure AI Search work together. And for that, but before that, let's talk about LlamaIndex itself. I've mentioned LlamaIndex several times without explaining what it is. So it's already obvious one thing which is it's a programming framework for creating generative AI apps. We exist in both Python and TypeScript, and we are open source and free to use. But that is not all that LlamaIndex does. One of the things we have that I've mentioned a couple of times already is LlamaParse. It is a service from LlamaIndex that will parse complicated documents in any format into a form that can be understood by an LLM. This turns out to be critical for a lot of Gen AI applications. If you are taking unstructured data like PDFs, Word documents, PowerPoints, things like that, and giving them to an LLM natively, it's going to have a lot of trouble understanding what it's looking at. LlamaParse can take things like tables, images, and various nested constructs and simplify them in a way that LLMs find easier to understand, and you will get demonstrably better results. We also have a service called Llama Cloud, which is our enterprise offering. I talked about the RAG pipeline, and Llama Cloud is a turnkey solution that connects to your data wherever it is, parses everything with LlamaParse for you, embeds your data, stores it in the vector store of your choice, and provides a retrieval endpoint, allowing you to then use the rest of LlamaIndex to build a first-class agentic AI application on top of that, without having to fuss over the basics. So why should you use LlamaIndex? At its heart, it's because we will help you go faster. You are an enterprise with limited time and resources. You have actual business and technology problems to solve. Don't get stuck on the basics. We have solved a bunch of the foundational problems of Gen AI apps for you, so you can focus on being novel and interesting and solving your actual business problem. Now to talk about how Azure AI Search fits into this picture, let's go back to Farzad.
Thanks, everyone. So now we're going to talk real quick about Azure AI Search. You've probably seen a couple of the announcements today or the past couple of days over at Ignite. But just a reminder for those who haven't used Azure AI Search, we're a revolutionary retrieval system. We have a bunch of different features in terms of most recently announced a new semantic ranker, a lot more powerful than what we GA'd 1 year ago. Highly recommend checking it out. Everyone gets it today, the latest and greatest. We also added a new feature called query rewriting. And fun fact, back in March, we actually partnered with LlamaIndex to actually show how, from using these open source orchestration and frameworks, how you can do query rewriting a lot faster. We saw a lot of customers using this with LlamaIndex and decided, you know what, I think we should bake this into our product. And that's exactly what we did today. So we launched a query rewriting engine as part of the semantic ranker, and we'll talk a little bit more about that. Streamlined data pipeline. We integrate with a bunch of other Azure AI services like the formerly known as Document Intelligence, now Content Understanding, as well as other AI services that you can use to further enrich your data. And then seamless developer integrations. That's what this partnership is about. We want to enable RAG everywhere. So through LlamaIndex, other open source frameworks like Semantic Kernel, and also recently announced this Ignite, RAG everywhere. We have RAG supported in GitHub, which we'll also talk about. Copilot Studio, you can now use Azure AI Search in Copilot Studio. And the flagship product recently announced this week as well, you can use Azure AI Search inside of Azure AI agents. And then, of course, what good is all these tools if you don't have a strong enterprise-ready foundation? And we're an Azure-grade service for being a vector store. When it comes to compliance, security, scale, we meet all those checkboxes as well. So going back, I want to quickly touch on the generative query engine. For those who haven't read this blog post at aka.ms/AI search-QR, I highly, highly, highly recommend reading it. We had our entire applied science team going really, really deep into how we actually built this. We took an open source construct from an advanced RAG technique, tested it with our customers, tested it with the market, with open source academic data sets, and baked this into our product. So again, you can use this with our new semantic re-ranking model, and not only do you get better relevance, you also get better latency. So we did a lot of optimizations, and our latency actually, query latency actually reduced as well. All right, and then a quick summary for those of you who probably don't want to read the blog, but I highly recommend. Here's kind of the one slider summarizing what this feature is really all about. 58% more relevant than vector search in our experiments that we ran that actually include of real Fortune 500 customers that we partnered with through data sharing agreements. And so you can see the progression of those different retrieval modes from vector using Azure OpenAI high, 3 large, hybrid, and then the hybrid with our new ranker that everyone has today, and of course with hybrid re-ranker with the new query rewriting engine, which really, really helps with the BM25 part of retrieval. Additionally, our new semantic ranker, this is already GA. It's a cross-encoder model that re-ranks the top 50 results, tested on over 90 data sets and across 19 languages, and we're only further expanding that for more languages and more variety of industries and data sets. And as I mentioned before, 0 configuration required. You automatically get that new re-ranker in Azure Search if you're using it today. Another announcement, RAG for GitHub models. So this is really, really cool, coming very soon. Azure AI Search will power RAG in the GitHub model marketplace. And so like GitHub models, it gives you the same easy access glide path from the playground to your IDE. So you can experiment with RAG on your own data in literally just a few clicks. So directly from the playground, all you have to do is simply upload your data, just drag and drop it as needed, and then a free Azure AI Search index will automatically be created for you. And so once you have that free Azure AI Search index, we've never launched some, we've had a free SKU before, but this is really cool because you don't need an Azure sub, you don't even need to put a credit card down, you just go crazy as a developer. And so I think that's super, super exciting for just getting your door into the capability of Azure AI Search. And here's a quick kind of GIF that shows kind of the experience. And if you want to sign up today, go to that link, fill out the Microsoft form at ak.ms/rag and GitHub, sign up. So cool. So with that, I gave a little bit of the sales pitch of kind of the new Azure AI Search features. But now let's actually go through kind of this whole topic is about advanced RAG. Okay, so what I want to show everyone today is actually how you can do advanced RAG. So I'm going to show a live demo. Let me switch my screen here. And I'm going to pull up my IDE. There we go. So over here, I have VS Code. And don't worry, you're more than happy to take pictures, but teaser, this code's going to be publicly available, and I'll show you the link at the end, so how you can access it and get started. So a hot topic when it comes to advanced RAG is on the topic of multimodality. Okay, so when you have a bunch of complex enterprise documents, you have PDFs, PowerPoints, whatever it may be, Excel tables, maybe mixed modality. And so how do you properly store that in a vector store? What tools are out there? Do I just do kind of naive chunking, use just regular parsing? Do I ignore the images, the tables, the figures, all that good stuff? So what I'm going to actually show today is a bunch of the things Laurie talked about. I'm going to show you how to take advantage of llama-parse with a very special announcement we actually have today with llama-parse for customers that use Azure OpenAI. And we'll leverage llama-parse. We'll leverage the Azure OpenAI service for a variety of different things in our RAG pipeline. And of course, we'll store our vector embeddings and perform retrieval in Azure AI Search. And we'll also use Azure Blob Storage to assist us with some of the outputs from llama-parse. Okay? So some key features, just like I showed earlier. In this case, we're going to have a very complex PDF. I'll show you just a few screenshots that have text, images of all different types of resolution, nested graphs, nested tables, charts, technical diagrams, you name it. And so what we're going to do is we're going to use llama-parse Premium to parse these documents that Laurie was talking about. And we'll use a very special edition of llama-parse Premium that I'll show shortly. We're also going to use vector search with Azure AI Search. For the demo, I'll just show vector search, but you're more than welcome to use some of our more advanced retrieval modes like hybrid search and the semantic ranker as well. And then very, very soon, we'll actually have the query rewriting built into LlamaIndex, so you can have your whole RAG pipeline, compare it side to side, and so on. And then, of course, what good is multimodal RAG without a large language model that you could actually use for grounding? Okay, so we're going to use GPT-4o for these multimodal experiences. Okay, I'm just going to zoom in a bit here. So setup and dependencies. So very lightweight Python client libraries that I'm using here. First one, Chainlit. I'm going to show a quick demo at the end that you could actually use to very, very easily have a user interface that you can demo to your stakeholders and do a POC, just in case this Jupyter notebook format doesn't really suffice for getting the job done. Okay? You also need LlamaIndex vector stores. In this case, I'm just, a lot of people ask me what version I'm using since it's constantly updating, so I'm just using 0.3.0, LlamaIndex Core, Azure Storage Blob, because we're going to store some images instead of blob storage, and python.env, just for some environment variables. Okay? Some imports, not going to spend too much time on this, but just all the different class libraries you need using the Azure Search Documents SDK, as well as LlamaIndex. You can see here Azure OpenAI Embedding, Azure AI Search Vector Store, and so on. Okay, so I'm just going to quickly run this. And then, of course, llama parse, the cool part. All right? And so optionally, a lot of customers ask how we can do kind of tracing when we get started. I highly recommend using this integration, this instrumentation baked into LlamaIndex with Arise Phoenix. And so very, very simple, literally in a couple lines of code. All you have to do is pass in LlamaIndex.core, set the global handler to Arise Phoenix, and you get really, really good traceability and observability tools. Just for demo purposes today, I'm going to skip that, but I had a few customers actually ask how do you do that in some other documentation that's been posted. Okay, so next up what I'm going to do is I'm going to initialize some variables here. So I have my Azure OpenAI endpoints, my chat completion deployed model, my embedding model, and my search service. So I'm not going to show how to do this, but simply go to the Azure portal, copy and paste, throw them in a .env file, and you're good to go by initializing them here. So I'm creating a search index called Azure AI Search RAG over here. I'm just going to use the settings.llm and settings.embed model. And so you can see here that's all I'm just setting up. I'm going to initialize my search clients over here, which is required for talking to Azure AI Search. And so the next step is pretty cool. Okay, so what I'm going to do is I have a bunch of documents, okay? And I'll show the data set in a bit, but it's a open source data set called State of AI by a company called Air Street Capital, where they published in 2024 what really is the state of AI. It's pretty much kind of a news kind of summary with a lot of visualizations and expert analysis from a venture capital firm, okay? So what I'm going to do is I'm actually going to show this PDF of data, images, state of the art. So what I'm going to do, I actually have the raw file over here. I'm just going to open it up so you can check it out, look at the types of contents. So just scroll through it, and you see some nested images, you see some nested tables, graphs, charts, quite small. So there's a lot of really, really interesting content in here. And so the question then comes, when I build a RAG pipeline, what's the correct way to model this? Is there models that I can use to verbalize or transcribe some of these images all to text? Are they multimodal embedding models that I can use to have a good representation? So all these mental models, as an AI engineer, you ask yourself these things. And so the cool thing about llama parse, this is what I love. I'll go back to my code over here. All I have to do is say, you know what, I know about reading about large language models, that putting it in a machine-friendly format like Markdown is statistically proven to help with answer synthesis. The language models, in this case GPT-4o, likes information when it's in Markdown format. It keeps some sort of structure to it, right? So what I'm going to do here, I'm going to set on llama parse, this class, use vendor multimodal model true. Okay, so now what I could do, if you set this to true, for customers in Azure, you could now add your Azure OpenAI endpoint over here with your deployed multimodal chat completion model. Okay, and so what I'm doing is I'm just passing in the endpoint over here, appending it to the API version. Then, of course, setting the API version again, and my Azure OpenAI key. Okay, so now what I'm doing is when I run this, just for time's sake, I already pre-processed it. In about 4 minutes, GPT-4o has scanned through my entire State of AI 2024 PDF. And what it's done here is, if you could look in the log, it's taken a screenshot, image for page 1. Okay, and so this isn't all that it's done. This is just printing out the image dictionaries, and it's saved all these screenshots locally. Okay, and so this is important because I want to take advantage of GPT-4o. And what's one capability of GPT-4o that's really cool? It's multimodal. It takes in text and images. Okay, so what this model is doing is it's parsing each slide into Markdown. That has a lot of cool features that Laurie talked about. And I'm also going to persist each of these images to blob storage. Okay, so what it's done here after llama parse, it's just, I've had this folder locally. You can see over here all these different image screenshots. Okay. So over here, what I'm going to do is just some code just to push all of these images to a blob container. Just because when I map this, when I ingest this to Azure AI Search, I actually want to have the image URLs that I can use. And of course, you can add SAS tokens and add security and all that good stuff. Use the power of blob storage. Okay, so I ran this code inside of my blob container. I have 212 images successfully uploaded. Okay. Next up, what I want to do is I want to create some text nodes, okay? Or think about that as just text chunks, okay? And so I just have some helper functions here just to really make sure that I have a nice clean schema that's really going to help my language model when it comes to grounding. So I set a function here to get the page number, okay? Because I want to display the page number of this PowerPoint or PDF. Get sorted blob URL, so this is just a kind of a utility function, and then actually getting the text nodes. This is essentially saying, hey, for all the markdown text that I just generated via llama parse, I want to go ahead and create a JSON metadata schema that's page number, image path, and the parse text markdown. Okay, so I went ahead and ran this. You can actually see here, this is the first page, which is actually quite blank. I have the page number, the image path, and then the parse text markdown. The first one, there was empty content, but we'll actually look at some with content in a bit. So now, next step, I actually want to take all this that I have locally inside of these variables and create a Azure AI Search vector store. Okay, so first thing at the top over here, I'm just defining my metadata fields. Metadata fields, some argued it's advanced RAG technique. Personally, I think it's table stakes, even for naive RAG. Metadata is so powerful. So I have page number, image path, and parse text markdown. And inside of Azure AI Search, I'll actually have these as metadata fields. And I could also filter on some of these. So what I'm going to do here is in LlamaIndex, use the Azure AI Search vector store class, pass in these properties. I just have a Boolean here because I'm just going to already create an index just for time purposes. Very lightweight schema, ID, parse text markdown, my vector embedding that this function is going to create the vector embeddings for each of these parse text markdown chunks. I'm using Azure OpenAI's text embedding 3 small, which is 1536 dimensions. My metadata string field key. In this case, I'm not really doing any kind of parent-child chunking, but if I wanted to, I could add a doc ID, which is kind of equivalent to a parent ID of a document. But for now, I'll just leave it here. It'll just be null. And then I want to say all my metadata fields that I defined earlier, I want them to be filterable. And then language, of course, because if I wanted to, I could perform hybrid search. And so having a language analyzer in Azure AI Search is really cool because for that full text search portion, you could define a language analyzer. In this case, I know my content, everything's in English, so I'm going to do English-Lucene, and then vector algorithm type. I have a relatively small data set, so you have 2 choices in Azure AI Search today. That's exhaustive KNN or HNSW. So I'm just going to go with exhaustive. Okay, so then what I'm going to do, I'm just going to create this new index, or actually technically because I have used existing index to false, it's actually going to create a new one, but I already have one, so I don't feel like paying again for my embeddings. So I ran this, and you can see here, in about 14 seconds, it generated vector embeddings for each of these text chunks. Okay, and so now we're gonna slowly see that in action. okay? So next up, what I need to do before I start actually doing the cool stuff with my RAG pipeline, this is where LlamaIndex is really, really shining, and it makes some of the built-in utility functions is really cool. So I want to create a custom multimodal query engine. Apologize for the typo there. So what I have here is I have a QA prompt. Okay, this is a prompt template. And I'm going to say to my language model, below we give parse text from slides and parse markdown format, as well as the image, okay? Dotted line, and then I'm going to dynamically bind my context string, so this is going to be my actual grounded information. And then I'm going to say, given the context provided, answer the query without relying on prior knowledge. Specify whether your answer was derived from the parsed markdown, raw text, or an image. If there are discrepancies between the sources, explain your reasoning for the final answer. Okay, so this is important because I want to, when I do my RAG evaluation, just with my naked eye right now, I want to see if it's worth it to the language model. Is it mainly paying attention to my parse text from llama parse, or is it deriving information from the image screenshot, okay? So I want it to help me out testing the LLM's thinking, okay? So I have my prompt template here. I'm just going to move relatively quick here. I have a custom query that's just creating the image nodes directly from the blob URL. So this is just cleaning things up, making sure I have my image URLs coming from blob to actually ground for answer synthesis, doing some formatting over here, and then ultimately getting the response with text nodes and image text chunks and image chunks, okay? And so here I'm going to initialize my GPT-4o multimodal model, very similar to what I did earlier. And yeah, we can go ahead and get started testing some queries. Okay, so this first query, what I'm going to do is I'm going to ask a question, and I purposely, this is advanced RAG, right? So I wanted to ask some pretty hard questions, not just like, what is AI, right? So in this case, I know the kind of content of this deck, and it goes really deep into AI research and kind of the key trends of 2024. And so I'm going to ask this question to start off. How did the 𝗦𝗲𝗀 and 𝗦𝗲𝗀 data sets perform using adversarial accuracy in different models? And how does this relate to training improvements for mobile clip in terms of image text pairing on smartphones? Okay, so lots of information in that query, but let's actually see what comes back, okay? So I'm actually going to run this in real time. And so what this is doing is I set a query engine above. If you actually see here in this multimodal query engine, it's taking my index that I just created. It's saying this is going to be your retriever in the retriever portion of RAG. And then the vector store query mode over here, I'm setting this to default. And the default's just a pure vector search. And I'm saying, hey, just give me back the top 3 nodes or chunks or images in this case. Okay? But if you want to get crazy, you could try out our hybrid and semantic hybrid search retrieval modes as well. Okay? So you could see here, because inside of my multimodal class function, I said, hey, make sure you state the query again. So there's my query that I asked. And you can see here are my retrieved images. It's a little small, but it talks about here. You could see here that in my slide deck, it's in the safety section, which makes sense, my first chunk or first node here, and it talks about adversarial attacks, okay? So this is getting in, and you can actually see the 𝗦𝗲𝗀 and 𝗦𝗲𝗀 bullet point over here on the bottom left, okay? So let's take a look at the response, okay? And I know we're not experts in this data set. It says achieve state-of-the-art adversarial accuracy using a method that combines blah, blah, blah. In contrast, mobile clip mentioned on page 23 focuses on improving image text pairing. While both methods aim to improve model performance, the former focuses on robust and image classification. So I think it does a pretty good job of answering this question. And then just to prove the source nodes, I'm not going to print out all the parse text markdown, but you can see here the exact page number that it's being retrieved, 184, 184, and then the length of the actual text, okay? So I'm going to do one more, and then we're actually going to go to a chainlet app to actually make this a little bit more sexy. All right? So what are the comparative benefits of using Sora space-time patches for video generation versus Vio's compressed video inputs in the diffusion process? So this is kind of a comparative analysis query. So there's probably going to be parts where the model, or the retriever in this case, has to kind of be smart about where it's pulling things from. Okay? So if I run this query, again, it's doing the exact same thing using the same multimodal query engine that I defined earlier. And so if anyone hasn't heard of Sora, it's the OpenAI research with video generation. Pretty cool stuff. And so you can see here, again, I have my image screenshots. You see some stuff about here with stable diffusion. In the first slide, you see in this first sub-bullet here, OpenAI Sora is able to generate videos, blah, blah, blah. So looks like I have a pretty good retrieval source. And you can see here the response. And in this example, it listened to my prompt, and it actually said these insights are derived from the parsed markdown text. So the model paid really good attention to the parsed markdown text here. But now let's do some fancy queries, okay? So what I'm going to do is I'm going to open up a terminal here, okay? And I am going to go ahead and run my Chainlit app, okay? And what this Chainlit app is going to do, it just allows you to visualize this a little bit better. And it's usually a good practice when you build these advanced RAG pipelines. A notebook is good, but having a way to visualize all the different things that are actually happening inside of your RAG pipeline step is a pretty good practice. Okay? So I have some sample questions here. I'm just going to show 2, and then we're going to wrap it up. So I'm going to say, what was OpenAI's GPT for model major dimensions of transparency for capabilities percentage? Well, I'll be nice and I'll actually, you know what, let's not be nice. Let's just say percentage. Okay, so what this Chainlit app is doing is it's actually going to show what's going on under the scenes inside of this advanced RAG pipeline. Okay, so you can see here this used retrieve step. So what is step 1? It's the input query string. Bam, you see it right here. What is the next step? The used LLM. Okay, so what's going on here? This is that custom multimodal engine that I said. So here's my prompt. Below, we give parsed text from slides in parsed markdown format, as well as the image. Let's see what those nodes look like. You have my page number 12 here. You have my image path, and you have the parsed text markdown, which over here, this is what llamaparse gave me. Pretty good. You can see here, this is a table in markdown format. We'll show the picture of the slide in a bit. But pretty good markdown representation that's been verbalized by GPT 4.0. And of course, my other chunks or nodes over here as well. Okay, so next up, I'm just going to quickly look. You could see here the parse markdown from page 195 provides information about OpenAI's transparency in various dimensions. For the capabilities dimension, OpenAI scored 100%. Okay, so now let's look at what this actually looks like. Okay, so you can see here, this is the table that GPT-4o parsed. Okay, so it has some stuff. I don't necessarily think this table had my ground truth, but we got the candidates over here. Okay, so this is a table I was looking at, and we'll show the raw slide in a bit. So you can see all these companies, the major dimension of transparency, and a capabilities row. Okay, so now I'm just going to quickly go down, and I'm actually going to show the screenshot of what was actually being retrieved. So you can see here in my second result, in my vector search, I'll just make this a little bit bigger. I'll open it up here for everyone to see. You can see that there is a table down here. Okay, this slide's talking about transparency, but how the heck did Azure OpenAI and Azure AI Search figure this out? That 100% is what I was looking for. So here's the table, and you saw that markdown representation earlier. Let's look on the y-axis, major dimensions of transparency. You see capabilities. Let's go until we see Azure or OpenAI. Boom, you see 100%. So that's pretty good, just understanding of a table. All right, so let's do one more example of kind of another multimodal dimension. So in 2024, what was the private public split for company AI valuations? And I actually didn't even intend typos, but let's see how it goes. So this is what's going on using retrieve. So it's retrieving those documents from Azure AI Search. And you can see here in 2024, the private and public split for AI company valuations was 2.2 trillion for private companies and 6.6 trillion for public companies. Okay, so here are my sources. I'm actually just going to go down to the images and see what's up. So let's look at this first image. Bam, looks like the correct slide that was retrieved, driven by public companies. AI companies reached nearly 9 trillion in a year. And I was looking for that private-public split. Let's look at year 2024 over here. What does that look like? Private, orange, 2.2 trillion. Blue, public, 6.7 trillion. So that's kind of a summary of how to use multimodal capabilities inside of Azure AI Search using LlamaIndex and llamaParse. So with that, I'm just going to conclude it. Here's the call to action. Thank you, everybody, for coming. Start building RAG solutions fast. Try out llamaParse with Azure AI Search and GPT-4o today. You want the code, go to that link at the bottom, aka.ms/AI search-llama. You can get all this. You can get started building today. Everything I just showed you is live. Thanks, everyone, and enjoy the rest of Ignite.